Great. So, good morning. I'm very excited today for today's class because finally, after weeks of doing preparation for data science, we are now entering into the world of data science. So, maybe a quick review of what we have done so far is we realized that to implement data analytics skills or whatever ideas we understand about analytics, to implement it on the system, we need to have some hands-on knowledge of Python programming. And in that journey, we started off with scratch basic Python programming. We covered operators, control structures, functions, modules, how to deal with different data science packages like NumPy, Pandas, Matplotlib, Seaborn, which we finished last class. Okay, so from now onwards, we are going deeper. We are changing gears into actual data science concepts. Today's class is very theoretical. We're talking about data preprocessing, and in the past, what I've done is, in the past, I have taken a real project, and during the study of the project, I stopped and discussed preprocessing. But I found that probably when we don't know the concepts, it becomes difficult to understand that example. So in this class, what I wish to do is first understand some idea of what data preprocessing is, what are the major steps, what is the philosophy behind it, and this will make us ready for the next series of classes that will come, where we actually take a real project. A real project means a study project of use case of sorts, and we'll see how we can apply these concepts of preprocessing on that project. Okay, so that's a fairly extensive project. I'm talking about the Titanic dataset. So if most beginners will start here, it's a very good thorough example of machine learning, classification, data preprocessing, and so on. So we'll study a data preprocessing, apply it on the Titanic dataset, take a break, study again machine learning concepts like supervised learning, and then we'll go back to the Titanic and try to complete it. Okay, so that will be the series of flow that will happen in the next few classes. Today we wish to cover data preprocessing. Okay, so that's the intro part. Do you have any questions before we start in this class? Okay, great. So let me go ahead and let us basically start asking questions like, why do we need to preprocess data? Okay. What is the need for preprocessing of data? And there are some answers. The primary thing is data in the real world is dirty. Okay, the data in the real world is dirty. By dirty, I mean data is incomplete, data is noisy, data has inconsistencies. Okay. So let's look at each of these. When we say data is incomplete, we're talking about missing attribute values. If you consider our ratings data set of we were discussing the movie lens data set when we were exploring pandas, and within the movie lens data set there was ratings, movies, and genres tags data, and we found that in one of those files, multiple values were missing. Okay? And that is the real world scenario, because there are multiple reasons why data could be missing when it finally comes to the hands of the data scientist, and now it's in your the ball is in your court and you want to implement your methods. You'll find that in many cases your data is missing. You have certain attribute missing, that is your sample may have few features, but it may lack certain other features. Okay, and in that situation, it's in your hand. What do you do? Do I ignore this data? Do I do something with this data that it becomes normal, so that I can give it to my algorithms and so on? So that is one part. Many of the times we will see that our data lack certain attributes of interest. Okay, so you started your analysis. You are hoping that you will train a machine learning algorithm that will be able to solve your problem, but you find that your machine learning algorithm is not able to do that. Okay, the reason it is not able to do that is your data does not have enough information for carrying out that task. Okay, So let's say I am designing a cooling system and I want to say what is the optimum temperature at which the mall cooling system should be at. Okay, and to decide that optimum temperature, I have several inputs. I have the size of the hall, I have the cooling units, I have the number of people inside. Okay, but let's say I can find out that we don't have proper sensors or we are not measuring temperature at key points in the mall that will give us some help. Okay, and you realize that okay, you lack certain attributes of interest. Okay, and that is also generally the case. Okay, many of the times you'll find out your data is incomplete, or at least the data that you have. You may have lots of data, but it may not be sufficient or relevant. Many of the times you also find that data only contains aggregate data. So instead of, let's say in the mall example, instead of having specific temperatures at different points, I have one common average temperature of the whole mall. Okay, and somehow whoever was collecting data assumed that this data may not be important, and they aggregated it. And by aggregating it, now I do not have eyes into different places. I have just one sensor. And that one sensor for the most part is not enough because mall being so huge, it may have a gradient of temperatures. Okay, and that temperature having just one value may not suit my purpose. Okay. Several reasons why data can be incomplete. So let's say many of the times when people are filling a form, you're filling the form for a bank, you're filling the form for applying something new, you may leave out certain criteria. Okay, or you may leave out, people may say that, okay, maybe this is not important and I will skip it. And what happens is by the time that data comes to the hands of data scientists, it is documented, the text is converted into digital format. You may end up with things like this. So someone has said occupation, not mentioned. Okay, and then you're stuck. You're stuck saying, what do I do with this point? Okay, how do I make use of it? So in the real world, we see that the data is dirty, that is, data is incomplete. Many of the times, data is also noisy. The data that you have, you are sure that this data is not right or that this data is wrong. So someone mentions a salary of -10, and you are like, we know that this cannot happen. Something is wrong in either in collection of data or interpretation of what we are trying to collect, or maybe it's a transmission issue when the data was being transformed from one form to the other. There were mistakes, and there could be hundreds of reasons why we have wrong data or noisy data, but we have to deal with such situations. Okay, there can also be something called as outliers. Outliers are most of your data you see follows a pattern, and it is having a certain range, and there may be some or very minor percentage of your data which is totally breaking that pattern. Okay, that it is showing huge variations between the numbers. Okay? And such data we call as outliers. We also call it as errors or noise, depending upon what situation you're looking at. Many of the times there are inconsistencies in the data. Okay, inconsistencies means there are you're collecting different features, and those features are contradicting each other. So let's say, for example, you have a row, you have a sample in which you have age given as 42 and birthday given as 1997. Okay, so given that we are in 2020, person would be around 13, 14 years old. It cannot be 12, 24, maybe, I don't know. Okay, definitely not 42. Okay, and such discrepancies in the data, when you find as a data scientist, you'll have to do something with it. You'll have to either normalize or ignore one of the data, or have some reasoning for giving preference to one or the other. It could also be that when, let's say, you're collecting ratings, and initially, when the system started or when they started to take the survey, they were taking the ratings as 1, 2, 3, and so on. And somehow in the future, the system modified to taking the ratings in A, B, C. Okay. So again, this is also an inconsistency in data. That is, your data is not the same throughout the life cycle of the collection. Okay. So you'll have to do something. I'm not saying this is an impossible problem to solve. So it's a fairly easy problem to solve, but it has to be dealt with. You cannot allow this data directly go to your machine learning algorithm because it will give very wrong results based on this. Okay. Or there can be discrepancies between duplicate records. You have records and you've got confirmation in multiple places, but the copies of the duplicate records are not exactly the same. There are some differences there. Okay. So these are few of the reasons why we need to pre-process data. Okay. So we asked why Pre-processing is important. Okay, so pre-processing is important because for a machine learning algorithm, when you give garbage, you will get out garbage. Okay, there is absolutely no way out of it. So I have here a small comic between a discussion between two people. So this guy is saying, "Are you sure the data you gave me is correct?" He says, "I've been giving you incorrect data for years. This is the first time you've asked." He says, "What can I see?" And then he says, rectifies, "I said the data is totally accurate." Okay. So what happens is, if you do not pre-process your data, you have absolutely no idea if the data you're feeding is wrong or incorrect. And you may feed it to your model, and the model will give you out some prediction, but we have uh, uh, very less confidence in the accuracy of that prediction. Okay, the prediction gives out something, but if you have not validated it well, if you have not tested it well, if you have not seen how things are, uh, uh, probably later down in the course, when you have deployed the model and the model is not working or it is giving very bad accuracies, that is the time you will find out that something is wrong. So unless we provide pre-processed clean data to your model, you can be sure that the model will give faulty or wrong results. Okay? So garbage in is garbage out. That's a very famous term among data scientists. That is why we spend a huge amount of time in cleaning data. So here, that is the next point. Our data collection, cleaning and preparation, it takes 80% of the time and budget. Okay? So throughout our entire journey of doing projects, we'll soon find out that we'll be spending a huge amount of our time just cleaning and collection and preparing our data so that we can feed it to the model. Okay. Feeding it to the model is very simple, and there are so many packages. And once we reach to that point, we'll understand that though that is the core part of data science, machine learning, we will see that we will spend a lot less time in machine learning. 80% of time will go in data collection, cleaning and preparation, and remaining 20% maybe we will focus in data analysis. Okay? Now, what are the major tasks in data pre-processing? So data pre-processing consists of multiple roles. Uh, we have data cleaning, we have integration, transformation, reduction, data discretization, and this is not the exhaustive list. Okay, there are many more things, and depending upon the need, we have to come across whether we will do a certain step or not, or some extra things are required before we reach to the training phase. Okay, so this is not an exhaustive list. These are the most common list probably. Okay, in most projects, we will come across this data. So data cleaning involves filling the missing values, smoothing noisy data, identifying or removing outliers and noisy data, and resolving inconsistencies. That is the first part of our project, data cleaning. First part, or maybe not the first part, or it is like it is a cycle. We do something, then we go back, we do something more, we go back, and so on. But it is a major step of our data pre-processing. Further, we look at data integration. So data integration is we have to integrate between multiple databases or files. So many of the times the data that you get in your hands may not be in one file. Some part may be in CSV files, some part may be in SQL databases. You may have access to some images of receipts. You may have access to some handwritten notes. You may have access to a data warehouse where you have pre-processed clean data. So you may have multiple sources of data. Your first job, your one of the primary job would be how would you plan to integrate all of this data or all of this into one schema that you can feed to your machine learning algorithm. Okay? Because your machine learning algorithm will not take data from multiple places unless you have broken down the machine learning process into several parts. But predominantly, we have one algorithm or a series of algorithms to do different things, and we'll have to get all of the data in one place. Okay, so that is also a huge task for the data scientist, okay, or data analyst, to take all of this and integrate into one common unified location. Then we have something called as data transformation. Data transformation includes a lot of things. Few of those is normalization, aggregation. So you will see that many of the time it would make a lot of sense if we can take multiple attributes, combine them to one, or combine raw attributes into something more high level and meaningful. Or many of the times we do normalization. That is, the different attributes may have different ranges of data. Let's say you're looking at your house prices data, and your house prices data has the square feet of a house. And the square feet of a house is 1500, 3000 square feet, it cannot more. And when you look at the rooms in the house, we will have maybe 5 rooms, 6 rooms, 7 rooms, 10 rooms at max. Okay. So this range is so different. Number of rooms, roughly about 10, the maximum is 10. And square feet is roughly around or greater than 1000. Okay. Because of this huge disparity in the data, your algorithm will not be able to generalize well. And that is why we have to do steps like normalization or aggregation, where we take all of this data and squash it into one range. Okay. Then we have problems like, or we have deal with data reduction. Okay. So you have to obtain a reduced representation in volume, but produce the same or similar analytical results. Okay. Many of the time, our data, or it again depends from case to case. Your data is so huge that you cannot do your analysis on it. Okay. We're talking about big data environments where the data is so huge that it becomes very difficult to visualize. It becomes very difficult to experiment with the data and so on. So what you would want in many of the times is you would want a smaller set, but this smaller set should be a representation of the bigger set. Okay, so a sampling of sorts where you have captured maybe 95% of the variance and so on. So data reduction steps helps us to do something like this. Then we look at data discretization, where we will try to take low-level data, raw data, and convert it into high-level concepts. Okay, so either by doing concepts or by taking intervals of the data and removing the noise, smoothing, binning, and so on. Those are the things we do in data discretization. Okay. Now, if you have any questions, you may stop me. You can ask me, okay? Because uh, I'm guessing probably these are pretty new concepts, and without examples, it will be difficult to understand. So if you face some difficulty, let me know. I'll try to explain this further, more simpler, giving more examples and so on. Anyways, let me go ahead. We'll look at each of these cases and we'll see how things will work out. Okay. So our first stop in our journey is looking at data cleaning, and data cleaning will deal with filling missing values, dealing with noisy data, correcting inconsistent data, and removing redundancy caused by data integration. Okay, let's look
Uh,
at
Elijah, just go back.
this.
Uh, how you fill the missing data? Just remove null. That what you mean? Or
Yes, my very next slide is going to talk about this.
okay,
So let's look at each of these, and we'll see. Or at this point, we are looking at some tips on how we will handle this in a real scenario. And once we actually come to the scenario, you'll find out that we'll have to do several things to see if our filling is valid or not. Okay. So how to handle missing data? Okay. So one option could be we simply ignore that tuple. So let's say uh, we have a database like this, and we have feature 1, we have feature 2, we have feature 3, and this is our final class that this is the class that we are trying to predict. And for each of these features you have multiple rows. Let's say we have row 1, 2, 3, 4, 5, 6, and once we get the data, you find that okay, I don't have feature 2 for 1, I don't have feature here, I don't have this data, I don't have this data. Okay. So we see that many of the times your tuple, we generally say this feature could be a representation of in a form of a tuple, and your tuple may have some attributes that are missing. So one option is that you ignore the tuples. That is, I say I will not use this data, or I will just delete this. So if I remove this out, remove this, and remove this, then I am out of 1, 2, 3, 4, 5. I am just left with 2 rows which are valid for my algorithm. Okay, it's a very bad it's a very bad solution, especially when you have less data. If I have maybe thousands and thousands of rows, if I skip out a few hundred, if I skip out a few 500s, okay, it will not matter to me because I have other relevant data that will help me give information about the physical system. Okay. But at this point of time, when you have less data, you ignore these tuples. It is going to harm my algorithm in terms of not having enough data. Okay, so let's say sometimes this is a valid solution, sometimes that is not a valid solution. Okay, let's go to the next step. Let's say we cannot ignore the tuples. Then how do I fill this data? Probably one question to ask before we go into these points is, why do we need to fill missing data? Okay, the primary reason why we need to fill missing data is this data will be fed to a machine learning algorithm. Okay, this will go to a machine learning algorithm, and this machine learning algorithm, once it finds missing data, it will break. It will not work out. Okay, so machine learning algorithms want consistent, clean data. Okay, and if you don't provide it, most algorithms will not work. In fact, I don't at this point, after knowing maybe tens, 15, 20 different algorithms, I don't know of any algorithm that will work with missing data. All of those algorithms will fail. Okay, so that makes it very clear that I cannot take this data and pass it to the algorithm. So we have to fill it somewhere. Either fill it or ignore it or remove it. But my machine learning algorithm should get all the data, all the attributes for each of the rows we are feeding to it. Okay. So now let me come back here. So ignoring may not be an option every time. Sometimes it may be an option. The other option is, let us fill this data. Okay. So if we want to fill this data, we can do it manually, but doing it manually is a very tedious or an infeasible option. Okay, especially in data science, we deal with thousands and thousands of rows of data. Okay, so it is impossible that we will go manually and we will try to fill each and every item. Okay, second, what do we fill the item with? Okay, so let's say we are talking about house prices, and in one place it is not mentioned how many rooms this house has. Okay, so how do you fill that data? Okay, so there can be methods for doing something like that, but doing it manually is very, very complex. Many of the times it is infeasible. So this is not a very good option unless your data is very simplistic, or you have hired people who would manually fill this data, and that is also an option. Many cases data scientists would, especially for surveys and things like that, when data is missing, they would hire people who would go around, do some groundwork, and then fill this data manually. Okay. Another, or the best solution that I have seen so far, depending again from case to case and depending on how most data scientists use, is we will fill it automatically. Okay, so we'll try to fill our missing values automatically. But when we say automatically, we'll have to provide some rules. By automatically, basically what I mean is, maybe automatically is not the right word. The right word would be programmatically. Okay, so we'll write a program that will fill this data. But to write a program to fill this data, we have to also answer what should be filled. Okay, what should be filled? And for that, there can be multiple solutions. This is not an exhaustive list. There are many more than this, but let's say we start with this. Okay? If I find a missing value, I will replace that missing value with a global constant. Okay, either I will say that this is unknown data. So instead of providing NA to my model, which says not a number, I will say this, let's say this is taking the number of houses. So I will say this is 5 houses, five rooms. Okay, and I will see that wherever it has missing data, I will replace with 5. Okay, now that will be wrong. Okay, but it will still allow me to feed the data to my machine learning algorithm. I may be populating with wrong data, but it will still allow me to run the algorithm. Okay? So from these 3 data points, instead of losing this and this also, I try to fill something suboptimal in this place so that I can use this one and this one as well. Okay. So that is one solution. We replace everything with the global constant. So we say feature 1 I replace with 5, feature 2 I replace with 10, feature 3 I replace with 3. Okay, replace with 3 means wherever there are missing values, only those values we will replace with this. Of course, where we have data, we will keep the same thing. And that is one option. We replace it with a global constant. This global constant can come from a domain expert. So depending on which domain you're dealing with, someone who has worked on that domain for multiple years may be able to give you a nominal good value that you would actually see. Instead of you filling something randomly, that the domain expert can give you some idea and give you some idea on what should be filled there. Okay, that is one solution. The other solution is we fill with the attribute mean. That means I want to find out what to fill this data with. I will say, let me take this one, this one, this one, and this one. And out of these 4 data, I find out what is the mean value. Okay. And from that mean or median or mode value, I will replace this guy. Okay, does that make sense? So we will use other parts of our data to fill the missing values of the data that we don't have. Okay? So that once we come out with the answer, our missing values would first be filled, and they would be filled with nominal values. They will not be filled with outliers, something that will actually change my model too much. We don't want that much. We don't want that missing values to be filled, but we'll put a common value that may not affect. So even if it is wrong, it may not affect my model too much. Okay, so that is another idea. We replace the attribute mean. Let me add more things. It can be mode, it can be median as well. Okay, depending upon your scenario. So uh, I hope, I think we've seen this before. We know the difference between mean, mode, and median. And you see, for categorical data, you cannot replace with mean. Categorical data means if my data says I have class, so I'm taking ratings, and my ratings can only take discrete values 0, 1, 2, 3, 4, 5. Then if I take the mean may turn out to be 3.73. Okay, then I cannot replace it with mean. I have to replace it with mode. That is what is the most common value. Or I have to do rounding on the mean, round it to either 4 or round it to either 3, and then fill that value. That is, we have to do certain things on the data before filling it out. Okay? And this could be a very useful solution. Okay? Replacing the missing values with attribute mean, mode, or median. Okay, and so this is also very easy. Uh, Even though easy, may not always be right. Okay, may not always be right. The third option is we can take an educated guess. Okay, how to fill the missing value? We can take an educated guess. Okay, and probably this does not seem very smart at this point, but when we look at our data, we can see that looking at other things, looking at other features, we may probably have a good idea of what to replace this value with. Okay, so I'm just taking an example. Let's say F2 is age and F3 is birthday. Okay, and even if this is missing, if I have this available, I can use this information and populate this. Okay, so we see that there is some relation with multiple features, and I can extrapolate that relation to be able to answer what should be filled. How should I be filling the missing values? Okay, so I can take educated guess. I can do heuristics. So have you heard this term before, heuristics? Okay. So heuristics is basically a very fancy way of talking about thumb rule. Okay. Most of us will have some idea of what is a thumb rule, right? So maybe let's say thumb rule for making rice is if I put 1 cup of rice, I need to put 2 cups of water. Okay. Is it accurate? Probably not. Does it depend upon the rice? Yes, it depends. Like how much water rice requires will depend upon the quality of rice. It will also depend upon how you are cooking the rice. Maybe you are cooking in a pressure cooker, or you're not using pressure cooker, and so on. Okay. But as a thumb rule, I know that double the amount of the rice quantity is a fair estimate of how much water is required. Okay, and this thumb rule would come from years of experience of maybe our parents, maybe some other people, chefs, and so on. May not be the right solution, but could work out very well when we don't know anything. Okay, that is what heuristics are. Heuristics are basically talking about thumb rules. Now, if I'm talking to a domain expert, the domain expert can give me some values of answers. So let's say if I have electrical data regarding AC voltages, and I have missing frequency information, then if I'm in India, I can fairly say that fill that information with 50 hertz. Okay. Now, someone not from this domain may not know what value to fill, but someone who has worked with this for multiple years knows that, okay, normally 50 hertz is not exactly right, because the frequency keeps changing between maybe 48, 50, 51, 52. But 50 is a very good estimate that we can fill it with. That is where heuristics comes. And other things maybe hints from the data and so on. So these are several ways where we could fill missing data depending upon different scenarios. Okay. Once we look into our data, Titanic data set, we'll find that there are multiple cases where we are missing values, and we will not use one solution for everything. Okay, we will use different solutions depending upon the scenario, depending on how much time we have, and there are other constraints that decide how we fill missing data. Okay. Anand, does that solve your question? Excellent. Let's go ahead with how do we deal with noisy data. Okay. So one way to deal with noisy data is we use a method called as binning. And what that binning helps us do, it helps us smooth data. So noisy data means I would have, say, normal data points like this, and I have one data point like this, or I have few variations, and then I have normal like this. So this is, would be samples of noisy data. I have most of my data in one line, but then I have few examples that go too much out of the range. Okay. And to deal with such noisy data, generally we could do different kind of binning methods. So here I've shown three different binning methods. So what we do with the data is, first we sort the data out. We sort it into one order so that we can see how the data is grouped and how it is changing. Okay. Once we have the sorted data, we can do something like this. We can do partitions into equi-sized bins. That is, we'll say, okay, there are how many elements here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 elements. So I can break it in 3 groups of 4. Okay. So I will partition into equi-sized bins. That is, we have bin 1, bin 2, bin 3. If you look at bin 1, we have ranges 4, 8, 9, 15. Bin 2, 21, 21, 24, 25. Bin 3, 26, 28, 29, 34. Now, within each bin, there is a lot of variation. So in this first bin, we have ranges from 4 to 15. Second bin, 21 to 25. Third bin, 26 to 34. Okay. So we have different ranges within the equi-size bins also. Okay. So if I don't want this noise, if I don't want this variance, I want simple data that may be enough for my model. One thing I could do is I could smooth them by bin means. Okay. That means I will take the mean out of the bin, find out which is the closest value, and replace all elements with that value. So instead of 4895, I'll replace everything with 9999. Okay. Instead of 21, 21, 24, 25, I replace that with 23, 23, 23, 23. So I replace the data with the mean of the data. Okay. And that is one option that we do to deal with noise in the data. We see that the noise is not important. Our model may not benefit from that noise. So we could smooth out the data. Okay. So that is one way, smoothing by mean or median or mode. That is one option. Other option is smoothing by bin boundaries. Okay. So I look at the boundary. So here the boundary is 4 and 15. Here the next case the boundary is 21, 25. Next case the boundary is 26, 34. So I can take the boundaries and you can say, okay, let me take all data points except for the last one and replace it with the minimum value. So okay, 4, 8, 9 become 4, 4, 4, and then 15 stays 15. 21, 21, 24 remains all 21s, and then we have 25. 26, 28, 29 remains 26, and then we have 34. So we are tying them to the boundaries. We can also do this. We can take the first two numbers and take it to the lower value, next two numbers and take it to the higher value of the range. Okay, that would also do binning by boundaries. So what these methods would do is they would remove out the noise from the data. Is this fine so far? Okay, let me go ahead. Noisy data is also called outliers at times. So noisy data means I am sure that the noise that I have in my model is not intrinsic to the model, but it has come because of some corruption in the data. Okay, but sometimes we can talk about outliers, and outliers are not corruption in the data. They are just inconsistent, or they are just very weird compared to the other data points that we have. Okay, so data points inconsistent with the majority of the data are called as outliers. We can have different outliers. So let's say we are taking the salaries of the people in an organization, and we see that most of the salaries they are they're coming in different groups, but one salary is completely different. It's something like CEO's salary. Okay, so there will be a huge amount of income, huge salary. Okay, and only one point of that salary, because there may be very few high-paying roles. And we'll see that this may seem like an outlier at first, or this may seem like a uh, uh, maybe an anomaly in the data, but this is actually a valid data because this corresponds to real salary. It is not noise. Whereas when you look at data like this, and we have age data, and someone has mentioned that their age is 200. Okay, we know for sure that this cannot be possible, and thus this is noisy data. Okay, so that's the difference between noise and outliers. Outliers are valid data points which are just different than majority of the data, and noise are invalid data points which cannot happen but has come into the data because of some mistake somewhere else. Okay, and to deal with noise or to deal with outliers, what we do is we use methods like clustering or curve fitting. Okay, so clustering would mean something like this. If I have my data like this in a two-dimensional space, I have majority of my data like this, and I have some data points maybe very far. This is not very clean. Let me take a probably a bigger pen. Okay. If majority of my data belongs, close to each other, and some of my data points are very far, then clearly for our analysis, this would seem like majority or normal data, whereas this would seem like outliers or variations in the data. And because of this, we may choose to say that data points that do not form inside this cluster, we have to deal with them. Okay, so either dealing with them by taking all of this, putting them together and taking a common value that is bringing them, or clustering them, removing them out, or trying to modify them and change them, update them to somewhere in the middle. Okay, and depending upon which scenario you're looking out, different solutions may be used, and different solutions may be valid as well. You can also use curve fitting methods. So let's say most of our data, looks like this. We are okay. We are following some curve. Okay, and we can see that probably uh, this would be the line that would fill this curve, and I have certain data points which look somewhere like here or somewhere here or somewhere here. Then what we could do is, since we know or since we have estimated a curve that represents other parts of our data, I can take this data point and I can push it down to this curve. I can take it and push it to the curve. Okay. So I can use methods like this to remove my outliers or to deal with outliers, again depending upon if this data is important or not. Sometimes it may so happen that majority of this nominal data is not of interest to us, and we are only interested in the outliers. In that case, at least this method will help us know what these outliers are, so that we can operate on them, we can do some analysis on them. Okay, so that was our data cleaning procedure. Uh, is it all right? Do you have any questions? Okay. Okay. Let me go ahead. Here we're talking about data integration, and data integration, as we talked earlier, is when we see our data coming from multiple sources and we try to put them together. Uh, so we are combining data from multiple sources. So generally, this happens, or this procedure happens in a data warehouse, where we will have defined uh, certain procedures or certain pipelines that the data should flow through before it is combined or merged together into the data warehouse. Okay, and many of the times, this is a fairly complicated step, and what may happen is in different companies, depending upon again how big the company is, how big the data is, you may have a dedicated role for a data mining expert who would be dealing with data integration. So the data scientist may not be directly involved in the procedure of data integration. Again, depending on case to case. If it's a huge company, they will have multiple people doing different parts. One part could be data mining. And if it's a smaller company, and smaller companies, generally you have to do everything from start to end, then I'm also guessing in those cases, the data will be fairly manageable. It is not so huge that a person cannot handle it. So we have to combine data from multiple sources. So this would mean doing series of steps. Okay. So let's say I have handwritten receipts or text from my organization. You would have steps like scanning them, getting them in the image format, trying to extract data from that image, populate a CSV file. That would be one part. Other part, those receipts, you may have bank records that will give you in Excel. Okay. Then taking the data from Excel and putting it again in a CSV or combining together would be would be the steps you would do for combining data with multiple sources from multiple sources. Another idea is schema integration. That is, all of the data is in one form. You have different CSV files, and different CSV files show you different features about the data. So if you remember, when we looked at the movie lens data, we had all of it could be called one big, huge data, unified data, but showing different aspects or different views of it. So you have one CSV that only talks about movies, genres, the year it was released, and that's it. Then you have another CSV that talks about different samples, user IDs and ratings that people have given. Another CSV, user IDs and tags that people have given, along with timestamps. Okay, so we have the data in one form, that is CSV format, CSV files, but they are divided into different files. Okay, so schema integration would be, how do I integrate metadata together? So we saw in pandas we could use the join method, uh, or concatenate method, and we could choose how do you want to join it. Do you want to use inner, you want to use left outer, left inner, left right outer, and so on, depending upon which one do you want to give more value to, and so on. Okay. So that is again a huge part in the data cleaning or data pre-processing step. We call it schema integration. Now, multiple times, once you integrate data, there may be value conflicts. Okay, so when you have a value conflict means one row is talking about, let's say you have two rows of data, maybe row one, row two, for feature one, feature two, and feature three, and we have a particular class. Okay, so here, let's say your the values are 1, 2, 3, and the class is A. Okay, and again we have the values 1, 2, 3, and the class is B. Now clearly this is some mess. Okay, why? Because we see that all the three features for the rows give same data. Okay, exactly the same features, but the final class is separate. Okay, now this could be either because someone could have collected the data wrongly. That could be one reason. Another reason could be there are hidden processes in between that we cannot see or that have not been measured. Maybe in the original scenario, we have more features like F4 or F5, which may have different values. Okay, and but we do not have eyes to see that because we don't have it in our data. This is missing for us, and if it is missing for us and we look at this data, we would see a conflict. The question is, how do you deal with that conflict? Do you ignore it? Do you take the majority? And again, those are things that we will have to think about when we are trying to integrate data and we find that there are conflicts like this. Now, there is no one solution to handle this part, and it will depend upon case to case. So once we explore data sets, we have to see why, or we have to try to estimate the process in why this must have happened. Okay. And once we try to estimate the process why this must have happened, that would help us to find out how we will solve the data. Okay. A huge part depends upon removing duplicates and redundant data. So removing duplicates and redundant data, you have multiple rows and all the rows are representing exact same values. Okay. Then what may happen is you may face another problem called as unbalance in data. Okay. So there are two classes that you're trying to predict for. Maybe you're trying to predict if an image is the image of a cat or a dog, and you've got 10,000 samples of cats, and you've got maybe 50 examples of dogs. Now, this is clearly unbalanced data. Okay. So there could be several reasons. One of the reasons why this unbalance would have come is someone has duplicated the image and Even though it is one image, we are showing it as 1,000 images or so on. Okay. So you would have to find out what the duplicates are. You have to find out what the redundant data is. So there is data, but that data is not adding any value to my model. In those cases, the data is not truly helpful, and we would want to remove this redundant data. So that is our data integration. Moving ahead, we look at data transformation. And data transformation, it would be not just normalization, there could be other things also involved, where we take the known range of our data and we try to squash it, or we try to change it, we try to modify it so that we have something more meaningful. Okay. Normalization is a very common step that we will use, and the purpose of normalization is my different features should be within similar ranges of information. So if I'm talking about feature F1, F2, and F3, and F1 varies from 0 to 5, F2 varies from minus 1,000 to maybe plus 10,000, and feature 3 varies from uh, 0.5 into 10 to the power minus 3 to 0.9 into 10 to the power minus 3. And if they have several different ranges of data, my algorithm may not understand which is what. So probably what it will do is it will say that this is the most important because this is the most wide range of data. And in comparison to this data, this and this would look like constant values. Okay, so my model will totally ignore F1 and F3 and give all importance to F2. Okay, which may not be what I want. Okay, and this would be the true ranges of my data, but my model will not understand that. So one way of solving that data is we can take representations of this data into a similar scale. So we convert them, all of them, into the same scale. Okay, to convert them into all of them into the same scale, we call this method as normalization or normalizing the data. So normalization can be done in multiple ways. Two ways I'm showing here. Something called as min-max normalization. The other called as z-score normalization. So min-max normalization basically says that if I have, let's say, a variable x, and that x is a variable between the values 3 to 5, and I want to change this value from 0 to 1, okay, I will have to do something called as min-max normalization. So what I will do with this data is I will say my new data x dash would be my old data x minus minimum value. So minimum value here would be 3. So x minus 3 divided by max minus min, which is 5 minus 3. That is the range of this max minus this min. Multiplied by new max minus new min. So new max is 1, new min is 0, 1 minus 0. So multiply this by 1. Okay.
Elijah, this is straight line equation, right?
Yes, this is straight line equation. And straight line equation is not like it is, what do you call it?
That x minus x1 by x2 minus x1 is equal to y minus y1 by y2 minus y1.
Yes, yes, yes. It is the same thing. I'm just thinking, I'm just trying to correlate how the straight line is trying to convert. Yeah, I probably understand.
Linearly.
Hmm. Yes, so let me fill this out and then I will
Yeah.
tell that. So plus new min would be 0. Okay. So by doing this operation, that is by just doing x minus 3 by 5 minus 3, what we have done is we have taken our data x, which would range from 3 to 5, and we have changed it to range from 0 to 1. Okay. Just as Anand was saying, I was thinking how to represent this. If you've got this, I will erase this part. Is this okay? Okay, so I'm guessing the formula is pretty straightforward. Let me delete this out. But remember the ranges, okay? Remember the ranges that we want x going from 3 to 5 to transform to x going from 0 to 1, okay? Now, as Anand rightly pointed, this is the equation uh, of a straight line. And you can imagine what is happening here is, let me draw x axis and y axis. Let's say on the x axis I have my range 3 to 5. And what I want to do is I want to transform this into the range 0 to 1. Okay. And this formula is giving me the slope. It is giving me the slope and it is giving me the intercept that will help me draw this line. Okay. This is my slope. This is my intercept. And this is my slope. Okay. And using this slope and intercept, I come out with, okay, to convert 3 to 5 to 0 to 2, I will have to draw this line. Okay. And this equation of the line comes from this formula. So for this equation of the line, I need y is equal to mx plus c. I have m and I have c. So I have formed this line. In fact, what we have found is we have found a means of converting the range from 3 to 5 to a range from 0 to 1. So any value between 3 to 5, let's say, okay, let's say this is a value that we want to convert. We'll go to this formula and we'll say, okay, this value of maybe 4 translates to this value of maybe 0.7. Okay, depending upon how that line is connected. Okay, this is where our formula links in together. You got this, Anand, right?
Yes, 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 yes. Got it.
Okay. So maths is only it's all about taking concepts we already understand and trying to look at them in different ways and try to see how we can apply them to different analysis and so on. So this is one option of converting, doing something called as min-max normalization. Other way of normalization is called as Z-score normalization. Many people, they call this method as standardization also. Okay, so they may not call it normalization, but they'll call it standardization. And what we do in that standardization is we take our data, we subtract the mean value, and we divide by the standard deviation. Okay, so this would be something like v minus mean. Mean is generally represented by mu, and standard deviation is represented by your sigma operator. Okay, so doing this operation will return to me v dash, and many times v dash is also called as z. Uh, Hence, it's called z-score normalization, z-score normalization. Okay, and this z is a very well-known term, especially when you talk about statistics. Okay, so you may have heard of Z charts, which help us to identify if certain data point, let's say if I have how much percentage of the data falls after 95%, how much data is between 20% and 90% and so on. So people use Z score for that analysis as well. We'll not go too much in detail for this part for now, but we can do normalization or standardization into this method. And this is also a very common method of taking all of our data and squashing it into one region. So that's very useful. And for both of these steps, for either you want to do min-max normalization or you want to do Z-score normalization, we have functions and we have methods available in many algorithms, in many packages. So you would not have to actually write it down, but you need to know that why this step is important and how you would do it. Okay. So let me see how many more slides do I have. Okay, we'll try to finish this off. The next part is data reduction. So data reduction is where we say that our data is too big to work with. There are too many instances and there are too many features. Okay. Too many features is also called as something called as curse of dimensionality. That is, our data is highly dimensional. That is, there are maybe 70 features, 80 features, and 70, 80 features is impossible for humans to understand. Okay. So that those are the reasons which will force us to do something called as data reduction. Okay, data reduction, that is trying to reduce our data into a smaller set. So, and the key idea here is we are trying to obtain a reduced representation of the data set that is much smaller in volume, but yet it produces the same or almost the same analytical results, which is very easy to say but very difficult to do. Okay, how do I take 10 million worth of data, transform that into 1,000 data points, which are still able to capture most of the information there in this 10 million data points? Okay? It's very complicated to do something like this, and but that is what we do in data reduction. Okay, so there are multiple strategies for data reduction. Two strategies would be something called as dimensionality reduction. That is, we try to reduce the dimensions. Okay, We try to, so if that data has maybe 70 features, we'll try to reduce that number of features to maybe 10 features, 5 features, and so on. So that is one idea, dimensionality reduction. We also have aggregation or clustering. That is, our data points are very far separately. So we will aggregate, cluster them together, and we will replace all of this with one data point. Okay. So that would be one part. There could be sampling. If I have a random distribution, I choose some samples for my analysis. I will not use all of them. Okay. So sampling could be another reason. So these are different strategies that we use for data reduction. Now, when we talk about dimensionality reduction, that is, we are trying to reduce the number of dimensions. This problem is also called as feature selection. Okay, so maybe uh, yes, Anand, if do you remember when we were dealing with generator data
Hmm?
for finding out faults, either main binding, this or so on. We had
Yes.
some 150, 160 different features. Okay, and is one. So we were working on a problem earlier where we were trying to find out the failure or the faults in a generator. Okay, we were looking at three different faults. Uh, let's call them fault one, fault two, fault three. And to identify this fault, we had collected raw data. Okay, so raw data would be the voltages VA, VB, VC, three-phase voltages of the generator, and IA, IB, IC, three-phase currents of the generator. And using this time series data, we generated lots of feature information. Something like, for each of the data, what is the minimum value? What is the maximum value? What is the mode? What is the RMS? What are the top frequency features of the data, and so on. So for each raw data, we had a list of, let's say, 10 different features that we will look at. Okay. So it was actually much more. It was around 30 different features. Okay. And 6 sensors, 30 features for each would translate to 180 features totally. Okay. Now 180 features is again some like we're talking we are in the range of curves of dimensionality. The data is so highly dimensional, it is very difficult for the model to learn anything out of it. Okay. So out of 180 features, let's say our model can work on very small set of features. We will have to choose which features we will give to our model. Okay. So this is the process of something called as feature selection. That is taking a huge set of features that is there in the data and trying to come to a subset that we will train our model with. Okay. So one method would be direct methods. Direct methods means find the minimum set of attributes sufficient for the task. Okay. So what I will do is, so here, since we understood how these faults were generated, we also understood that these faults would represent themselves into the frequency information. So out of these 180 features, we had a list of features. We would say that probably these features are important for the data compared to other ones. So we will handpick them up. We will say, okay, let me take first harmonic, let me take fifth harmonic, let me take RMS. Okay, so we would handpick this data. And once we have this smaller representation, we will use that to train the model. And after training the model, we'll look at its accuracy. Okay, so let's say after training with just three features, my accuracy is 80%, which is fairly good. Okay, I will increase the list to 10, and after taking 10, my accuracy is 97%. Okay, and let's say my application requires 95% or more accuracy, then I will stop at 10 features. I will not take all 180 features and work them out. All the 180 features will add very less value to my model. At the same time, it will be very bulky. At the same time, it will be very costly to implement it. Okay. So based on these ideas, we could use direct methods, which helps us select the sufficient attributes, which will be enough for our calculation. Okay. So sometimes this direct methods can involve the domain expert who could say which features will be of value, which will not be of value. That is one idea. Or we can have automated methods that will do feature selection, feature ranking. Okay. So we have algorithms like ANOVA that help us do feature ranking. We have also some more algorithms. I don't remember at the moment. Maybe later on we will look at it. And those ranking methods can be used to find out which are more important, which are less important, and then we can use them for our dimensionality reduction. There are also indirect methods which will take all of this data and it will automatically try to find out, or what it will do is it will automatically take 180 features and say, I will give you top 5 features, which will contain 95% of the variation of this data. Okay. And those methods are principal component analysis, PCA. So we will look into PCA when we do something called as unsupervised learning. Later down in the course, we'll look at unsupervised learning, where we will use some of these methods to get a smaller representation of a data. So PCA is a very common method. We have something called as SVD, singular value decomposition. If you have dealt with linear algebra, we use SVD to find eigenvalues. Okay, that is again something that some of us may have some idea of. Then there is something called as independent component analysis. Okay. This is also a very interesting method. We don't have time or space to understand this, but these are indirect methods which will help us to take a huge set of features and to give us a small set of features which represents most of the data. Our last step, I quickly finished the data discretization. That is, when we have different types of data, nominal, ordinal, or continuous. Nominal data is values from unordered set. So unordered set, like I'm saying item number 1, item 2, item 3, item 4 of the different objects in a supermarket. Okay. Now these items, even though I'm attaching 1, 2, 3, 4, there is no correlation between these numbers. 1 is not smaller than 2, is not smaller than 3, and so on. Okay. Why? Because they're representing IDs or identification. Okay. And identification in that sense is unordered. Or we can have ordinal values. Ordinal values like rating of it, ratings, right? Ratings 1, 2, 3, 4, 5. Now same numbers 1, 2, 3, 5, 1, 2, 3, 4, 5 have meaning. 1 is less than 2, is less than 3, is less than 4, is less than 5, right? That is called as ordinal type of data. Or we have continuous data. That is, they are going from going in a what do we say, in a continuous fashion. Now we can take this data and do discretization. The purpose of discretization would be to make the model simpler so that it can understand, or we could do discretization for removing noise as well, for smoothing, for removing outliers, and so on. So discretization method would say divide the range of attributes into intervals and replace those intervals by a common value. It's very similar to what we saw earlier in binning. So let me not talk much about this. Let me talk about concept hierarchies. Concept hierarchies are when we take low-level concepts and convert them to high-level concepts. So let's say that we have one feature that gives us the age of a person in numbers. Okay, we have the age of a person in how many years old that person is. So this data would be probably very difficult for my model to understand, or maybe complex enough for my model to understand, depending upon if it is needed or not. But I could take this and convert them into high-level concepts. High-level concepts like, is given a range of numbers, is that person a child? Is he youth? Is he an adult? Is he a senior? Okay. So now this is a high-level concept that depends upon age, but is not as granular as age. It is more of an abstract, or more of a, what do you say, more of a clustered condensed form of the data. Okay. So that is what we do with concept hierarchies. And we'll see in Titanic dataset, we'll be dealing with this as well. So to finally summarize, we see that data preprocessing is a big issue for data science projects. Okay? As we will spend 80% of our time doing data cleaning, collection, and preparation, and 20% of time in actual analysis. The major tasks are cleaning, integration, reduction, feature selection, discretization, etc. There are many proposed methods, but still it's an active area of research. So if you ask any data scientist, what is the best method to do? No one will be able to give you an answer. Okay, it all depends upon several questions. Okay, and it is also some area that is highly being researched. So there are many people who are trying to find out, can there be automated ways that we can reduce this step down, or we can do it simply, or we can do it in a simpler fashion, because 80% of the time is a huge amount of time that we're spending on cleaning. So if we have better methods of doing it, it will be much better. Okay. So there is an active area of research. And many of the times, our analysis or the way that we will do data preprocessing depends upon the data, and it's an art. So when I say it's an art, when you talk about two scientists, will they come to the same solution? Definitely not. different scientists will have different solutions to it. And it's like not a formula that you put in and everything works out. It depends upon people, how we analyze, how much intuition we have into the data, how much experience we have with data. Can we predict a step that we do now? How it will affect our entire pipeline and so on. So those are key things that we look at when we do data preprocessing. Okay. Do you have any questions? Okay. Okay. Great. So with this we will stop this class, and next class what we will do is we will look at the Titanic dataset. I have talked a lot about I mentioned this multiple times because probably I love this dataset because it was my first dataset, my first serious dataset that I explored a lot of time into. So we will take these ideas of data preprocessing and we'll see how we can apply those ideas into a real setting and how it helps us to clean data or keep it ready so that we can feed it to our machine learning model. Okay. Okay. So I will stop recording and we'll